Welcome to Introduction to Quantum Field Theory, Lecture 19. In this lecture, I will continue the discussion on thermal phase transitions in quantum field theories. Recall that in the last lecture, Lecture 18, we considered a quantum field theory with a scalar field that has a potential with a negative mass squared or an imaginary mass. We found that using the mean field approximation, that this potential gives rise to a phenomenon that's known as a thermal phase transition, where the theory is in a different phase at low temperatures than it is at high temperatures. In the last lecture, we found that the phase that the theory is in was controlled by the minimum of the effective potential, VEF, that is defined implicitly through the definition given in equation 19.2, where the partition function for the theory is given as an ordinary integral over the mean field times the exponential of minus beta times the volume times the effective potential. We also found that in the mean field approximation, the effective potential was just given by the expression for the classical potential evaluated at the mean field. In this lecture now, we will put the study of the thermal phase transitions on a more rigorous footing. We again start by decomposing the scalar field into two parts, namely a constant part, which we denote as phi bar, and the fluctuations, which we denote as phi prime. Because we want to put the whole constant part of the field into phi bar, the fluctuations by definition obey that the integral over the fluctuations will just give 0. If we use this decomposition, we find that the potential evaluated at the field phi falls into two parts. It's given as the potential evaluated at the mean field, plus terms linear in the fluctuations, plus terms quadratic in the fluctuations, plus terms cubic in the fluctuations, plus a term that is quartic in the fluctuations. Now, since the fluctuations fulfill that the integral over them just vanishes, in the action, the integral over the potential will lead to the effect that the linear fluctuation part just drops out because the integral over phi prime just vanishes. So in the action, we are left with all the other parts, namely the classical potential evaluated at the mean field and terms quadratic, cubic, and quartic in fluctuations. So after the decomposition, we have an expression for the partition function that is given in equation 19.5. The partition function is given as the integral over the mean field times the exponential of the classical potential times the path integral over the fluctuations over two expressions that involve the some sort of modified action, which I denote by the prime, where these two expressions are S0 prime be given by the quadratic part in the fluctuations. So that has a kinetic term and it has the quadratic part of the potential. And a second term that I call Si prime, which has the cubic and quartic contributions in fluctuations. If we do that, then we find that if we look at the expression for S0 prime, that looks just like the non-interacting contribution from the quantum field theory with an effective mass, the effective mass being given by these two terms that multiply the term quadratic in fluctuations. And it's an effective mass because it depends on an external parameter phi prime, but otherwise this dependence doesn't really sort of complicate the calculation because for the path integral expression, we can treat phi bar to be an external parameter. Once we rewrite this in terms of an effective mass, the action S0 prime looks just like the free action for the field theories that we have studied before. And we can use perturbation theory to calculate the effect of including the SI prime contribution in the action over that the path integral for the fluctuations are integrated over. By construction, if the expectation value of the mean field is vanishing, the calculation for the fluctuations just reverts to the standard perturbation theory. We will refer to this case as the symmetric phase. And by contrast, if the mean field is non-zero, the calculation is modified because there's a non-vanishing expectation value for the field. And we will refer to this as the broken phase. Now, the theory itself has to tell us which of the phases is actually realized at which temperature. So now that we've set up the nomenclature, if you will, let us now calculate the effect from integrating out the fluctuations on the effective action in the perturbation theory. So we start by just doing perturbation theory by sort of ignoring the interaction term SI completely, and then we have an integration over the fields with essentially a free action as not prime, where just the mass parameter is non-standard. Since the action S naught prime is quadratic in the fluctuation field phi prime that we're integrating over, we can just reuse our result from free field theory in lecture 9. The only modification is now that the mass parameter is an effective mass that depends on the external parameter phi bar. So then, using the results from lecture 9 and lecture 10, we have that the path integral over phi prime of the action S naught prime is just given as an exponential of an ordinary integral over an expression that involves ek, which was defined as the square root of k squared plus m squared. And that is nothing else but the exponent of beta times the volume times the free pressure at temperature T. And we have calculated the renormalized free pressure in the MS bar scheme in lecture 11, so we can also reuse the result from there. So using equation 11.16 from lecture 11, we find that to leading order in perturbation theory, the pressure and hence the renormalized effective potential is given by the following expression. It's given by the classical potential evaluated at the mean field. And then there are two terms that come from the renormalized pressure that we've written down in equation 19.10. One of them is a sort of zero temperature contribution, and the other one is a thermal contribution to the pressure. Let us now look at what this result implies. And to get started, we choose to study the zero temperature case, in which case the function jb just vanishes. So this just simplifies the discussion. We also have to choose a value for the renormalization scale mu bar, and we choose mu bar squared being m squared, the mass of the original problem. So using those choices, we find that the perturbative effective potential to leading order perturbation theory is just given as the sum of these two terms. And it is maybe illustrative to compare this result to just the mean field approximation, which is just the leading term here, for a specific value of the coupling constant. So we can set lambda to 1, and we'll find what the corresponding result is. It may seem strange that we have to choose a value for lambda, given that there is no lambda appearing explicitly in equation 19.12, but the lambda, the coupling constant, appears implicitly through the expression of the effective mass. Let me just go back one slide, sorry, 2 slides, where we have an expression for the effective mass here that indeed involves the coupling constant lambda. So now, choosing a specific value for the coupling constant lambda, we can just compare these two results And this is the result that we find, that we have the potential as a function of the value of the field. The mean fit result is given as the full line here, and the leading order perturbative result, PT standing for perturbative, at low temperature, meaning 0 temperature, is given as the dashed result here. And you can see that there's certainly no qualitative change and not even much of a quantitative change from the mean field result to the leading order perturbative result. Let us now reverse course, and instead of studying 0 temperature, let's study the high temperature limit, meaning temperatures T that are much, much larger than the mass m. To analyze the effective potential, it would be good to have an expansion of the function JB in powers of the mass m compared to the temperature T. We can actually, again, reuse some of our results in previous lectures to glean a result for JB that we can use for our purpose. Specifically, the leading order in the expansion of small mass of this function JB was given in equation 11.5. And the next leading order term can be gleaned from equations 15.17 and 15.18. Long story short, if we put together these results that we already calculated in previous lectures, we find that the expansion of JB up to quadratic order in the mass is given by these two terms, where higher order terms involve higher order powers of the mass. We have to recall that we have to evaluate this result not at the original mass in the Lagrangian, but the effective mass that involves the field phi bar. And if we do so, we find that the effective renormalized potential at high temperature is given by this expression here. Again, we have ignored contributions that are higher order in m. We can again try to visualize this result compared to just the mean field result if we again set mu bar to be equal to m and the coupling constant lambda equal to 1. And we find the following result. This is again the potential as a function of the field phi. This is the mean field result that we discussed before. And here is the leading order perturbative result at high temperature. This is the dashed line here. What you should notice when you compare these two curves is that indeed there is a qualitative change from the mean field result at high temperature in the fact that the high temperature perturbative result does not have a minimum except for phi of 0. So it's a symmetric potential, and that means that at high temperature the symmetry is indeed restored, which is something that we already argued for in the last lecture. The reason that the symmetry is restored is that at high temperature the quadratic term in the effective potential becomes positive because the temperature dependent effect dominates over the minus m squared. We can look at the explicit expression in 1914 where we have the quadratic part in the field phi bar, and the coefficient of this is given as the minus m squared plus lambda t squared. And you can see if lambda t squared is large enough, it will change the sign of the quadratic term, and that will make the potential, instead of curving downwards from the origin, curve upwards from the origin, and there's no longer any symmetry breaking. So we find that at high temperature, the minimum of potential is located at a phi bar is 0. And therefore, at the high temperature phase, the expectation value of the field is 0, and we are in the symmetric phase. We can do more than this. We can estimate the location of the phase transition between the low temperature and the high temperature phase in perturbation theory. And to estimate the transition temperature, we can start by looking at the location of the minimum of the potential. So we calculate the derivative of the potential. If we wanted to look for a minimum, the derivative of the potential would have to be equal to 0. We calculate this derivative and we set mu bar is equal to m. And we want to track the existence of a symmetric phase, so where the minimum of the potential is located at phi bar is 0. So if you plug this in, we find that the derivative of phi bar is equal to this expression in 19.15. And if we then say that a minimum of the potential would have to be given if this expression is equal to 0, we find a result for the critical temperature at which the minimum potential is just given by the symmetric phase at phi bar is 0. So we find that the critical temperature squared has to be given by the expression in 19.16. And 19.16 contains two terms. One is 1 over lambda, and then there's a constant offset. However, we are doing perturbation theory, meaning that we are expanding around the case of very small lambda. So we, by consistency, basically have to ignore the constant offset to leading order in perturbation theory. So we find that we can expand the right-hand result in powers of lambda and find that to leading order in perturbation theory, the critical temperature is just given as m over the square root of the coupling constant. And this concludes the present lecture.